jot down some drawings and make some comments about how I view the operation of a transistor. So let me select a normal brush size and then select a good color. So this blue, as you can see, my drawings aren't that great, but I'm going to try to show how this works. So this symbol, the NPN transistor, this is the emitter, N-type material, base P, and collector N. And what's it take to make this device work? Well, you have to forward bias the base emitter diode, meaning the base has to be more positive than the emitter, and the collector has to be reverse bias with regard to the base, meaning it's more positive than the base. So what happens when this device is on? Well, the current through the base controls the collector current, and as it turns out, the emitter sees both the base current and the collector current. So when I think of this, I always think that the electrons flow from a lower potential to a higher. So if this device is on, the emitter current, some of it will go through the emitter base junction and out. Like we said, the current goes from a lower potential to a higher, and then at the junction some of that current will go through the collector leg. So if you recall, Kirchhoff's current laws tells us that the sum of the current into a node has to equal the algebraic sum of the currents out. So the emitter current is equal to the sum of the base and the collector. So how do we get this device to work in the real world? Generally, transistor circuits are thought of in terms of DC bias, as well as how do they work in the AC environment. So I'm just going to draw a simple circuit, and I'm going to use rectangles for the resistors. It just seems easier to draw. And resistor in the emitter leg. We'll set this up with some voltage divider bias to establish the DC operating parameters of this circuit. Alright, so if we call this resistor R1 and this one R2, call this R collector and R emitter. Alright, standard voltage divider bias. So we said to get this circuit to operate it, for the transistor to turn on, you need some base current, and that the current in the collector will be amplified by some amount. That term is called forward current gain. Most data sheets you'll see something like this: HFE, forward current gain, or DC, current gain. In this case, we want to know what's the voltage at the base. And the standard convention for voltages around this type circuit are that if you have a capital letter such as V sub E, that means what's the voltage at the emitter with respect to ground. VB, capital B, voltage at the base with respect to ground, and VC, capital C, voltage at the collector with regard to ground. So what is the voltage at the base? Well, this is just a voltage divider. Let's say that this is some arbitrary voltage, Vs, voltage from the source, and the voltage at the base then is a diode drop above the voltage at the emitter. So I think for the purposes of this explanation, I'm going to place this emitter at ground, which will just make it easier to do our calculations. Alright, so what is the voltage at the base? Well, VB is equal to the percentage of resistance R2 is to the total in that chain, which is R1 plus R2, or the ratio of R2 to the total in that chain, times the source voltage. So we could give this some values if we like. We could say that R1 is equal to I don't know, let's say it's 2K ohms, and R2 is 5K ohms, right? So what happens with this problem? Well, we end up with, and to make this even simpler, I'm going to put this back, which will help. We'll just call this RE. So what is the voltage at the base? Well, it's 5K. Again, this is ohms over 5K plus 2K ohms times Vs. We'll say Vs is equal to 5 volts. 5 volts, and we get 5 over 7 times 5 equals 25 over 7 equals 3, and about 4/7 volts. 4/7 volts.